We are going to discuss about the practice exam. And as you know, the first midterm is next Thursday, and we have 24 hours time window for you to solve the questions. But I expect maybe you only need like 2 hours for that. And the materials for the the midterm 1 is from lecture 1 to lecture 8. And actually, we will have another review session maybe next Tuesday in class, online. And then we will review some of the key concepts for the first midterm. But today we are going to take this opportunity to, let's say, do the practice exam. And this is from one of the earlier semesters. So we will have a similar format for your first midterm this semester. And the first question will be this like true or false question. And then here we have 10 questions. So we can go with those questions one by one. I will read the statement and then give you maybe 20 seconds. And then you can ask yourself whether this is true or false. So here we don't require the reasons for true or false. We just look at the statement. If the statement is partially false, then it's a false, okay? Unless the statement is completely true. All right, so let's get started. So the first statement here, in an intrinsic semiconductor, the carrier density Ni increases with the increase of the temperature. So is this true or false? I'll give you 20 seconds. And also you can type in your answers from the chat if you wish. So it's a true or false. So what's your name, by the way? Okay, so is true or false? What's your answer? True, okay, and also I got some answers online. It's true, yeah, that's correct. So here in the intrinsic semiconductor, as we know, intrinsic means no doping, right? So then the way to generate the carrier electron or hole is by the thermal vibration. So if you have higher temperature, then you will have more chances to break the bond, and then you will get more electrons or holes. And the electron density will equal to the hole density in this case, and this is called Ni. And also, if you want to look at the equation, I think we provide some equations at the end of the exam sheet. So for example, here the intrinsic carrier density Ni is given by this formula, and you say this is to the exponential band gap, negative band gap over 2 kBt. And you see that if you increase the temperature, then this is in the denominator, so this whole term will be reduced. And then you have a negative sign. If you increase temperature, then this whole term will be reduced, and then you have a negative sign. So you actually is increasing the overall exponential term. Okay, so this is true. Let's go back to the second one. The diffusion current is proportional to the gradient of the carrier density. Okay, so how about this one? Let's say 20 seconds. Any answers from the chat? Okay, I think this one is also true. The reason is that if you recall the diffusion current, we don't have it here, but I will provide, let's say, let me find it. I'll provide this in the exam folder. You see there is a PDF file with the equations like this. So this is in the exam folder on Canvas. And you can find the key equations here. So the diffusion, right? So diffusion, this diffusion current is proportional to this, the gradient dN over dx. So this is true. Okay. Then let's go back. Oh, where is it? Where is my? Okay, the third one. The drift current is proportional to the electric field and the carrier density. Is this true or false? 20 seconds. Okay, drift current. You can go to the same equation in that equation sheet as here. The first term is drift, right? Drift is proportional to the N carrier density, in this case, electron, and then electric field, E, and of course the mobility. So this statement is true. Okay, this is also true. How about the fourth one? Metal A has a smaller conductivity than metal B. Which one would you use as a metal interconnect? A or B? $20 seconds. Okay, so for interconnect, we prefer lower resistivity because the resistance is smaller, then the RC delay will be smaller. So smaller resistivity means higher conductivity. So then we prefer metal B, right? A has smaller conductivity, B has larger. So in this case, we prefer metal B. So let me see if I can. Yeah, I can. Okay, any questions? Okay, number 5. Group 3 materials are used as donor dopants to make the silicon N-type. True or false? N-type, we need donor. That's correct. You donate the electrons. But we don't want group 3 because group 3, you have one less electron than group 4. So actually you need to accept electron in group 3 material. So this is false. To make a silicon N-type, we need to use group 5 material, for example, phosphorus. So this is false. And number 6, in a p-type semiconductor, the Fermi level is closer to the valence band or conduction band? Which one? P-type. Fermi level is closer to which? If you recall the band diagram, we have Fermi level, and we said that Fermi level closer to the EV, the valence band, the semiconductor is P-type. So this is valence band. Okay, number 7. In a p-n junction, the depletion width increases with the increase in the forward bias voltage. So this one may be tricky. Depletion width. So what is depletion width first? P-n junction. We have P-type interface with N-type. Those electron and hole will recombine with each other. So in the middle, there will be a region where the carriers are depleted. And then maybe we can go back to lecture 7. I think one good news for this virtual exam is you can go back to the lecture slides and textbook to refer to those. In the normal settings, we have the classroom exam, then we only allow like a 1 or 2 page hit sheet normally. But this semester, we will allow this. So then you can go back to lecture 7. So we are talking about what here? We are talking about this one. Right. So this is let's say forward bias. Let me see, where is it? Yeah, here, forward bias. And then with forward bias, you see the animation here. Because you are going to inject the holes from the positive terminal and then extract the electrons to the, inject the electrons from the negative terminal. So effectively, the depletion width will be reduced in forward bias. Okay. If you play the animation, then you will find out this one. So here will decrease, right? So then this is wrong. Any questions so far? Number 8. The drift current in N-type silicon decreases with increasing donor density given the same applied voltage. So the drift current, okay, in N-type and donor density. So the drift current here, you see N-type, that is electron. So you have this Q N mu N E. So if N increase, current increase, and this N is electron density. And in N-type, this electron density is given by the donor density. So then if donor density increase, electron density increase, and the drift current increase, right? So then this one is false because it says decrease. And number 9, how does the threshold voltage Vt in a MOSFET change with increase of the body doping density Na? So this is like an N-type MOSFET. So your doping is P-type to the substrate Na. So the threshold voltage Vt, increase or decrease? This is what we just discussed in lecture 8. Any answers from the chat? Increase or decrease? You can always go to, if you like the equations, then you can always go to this sheet. You see here, threshold voltage, right? We derived this in class. First has a square root term, and then 2 phi b. So in the square root, we have Na here. So if Na increase, then Vt increase. And also the phi b depends on Na actually. And if you recall the lecture 8, phi b is also correlated to the Na. And also it's here. Phi b also depends on Na, but it's in positive relationship. If Na increase, phi b increase. So Na increase, phi b increase. And then if you go back to the threshold equation here, then both terms increase with larger Na. So threshold voltage increase. Okay. This is increase. And number 10, in the MOS cap, surface potential phi s becomes almost constant at 2 phi b for the gate voltage larger than threshold. Is this true? Lecture 8. We showed some animation at the end, and we have the here. This one is the where is the phi b? Phi b is a bending here. So it's this is surface of the silicon. So this is a phi s. Sorry, we're asking about the phi s. The phi s, when you increase the gate voltage, the phi s keep increasing. This one keep increasing. Here, this is threshold condition, phi s equals to phi b. So here is phi s equals to 2 phi b. But after that, if you further increase the Vg, you see this point almost no change. The additional gate voltage you apply will drop across this Vox. This is phi s. So this is true. When you further increase the gate voltage above the threshold, the silicon surface is almost pinned at this 2 phi b. And then the additional gate voltage drop on Vox, the oxide. Okay. So those are the concepts. So the true or false question, if you see here, so mostly are the concepts. So you should expect similar questions in the real exam. All right, any questions? Yeah, increase. Okay, so then let's move on to the second question. So this is on a MOS capacitor. When this is NMOS with p-type doping, and then the doping density is given Na 10 to power 17. So the first question, what are the electron density and hole density at the surface, the semiconductor and oxide interface, when gate voltage equals to 0? So if you recall the band diagram for the MOS cap, we are asking you at 0 voltage, then you know it's equilibrium. So the EF in the metal and the EF in the semiconductor should be aligned. And this is a p-type substrate. So you know it's something like this. The EVEC. And then it asks, what is the at the surface? This is the surface. And this surface, what is N and what is P? So I'll give you a few minutes on this one. At the surface here. Okay, so let's think about this. So this is at the equilibrium state. So then it's like a p-type semiconductor in the substrate. Then you know we have more holes because we have Na. So then the P should be the same as Na, right? Because here we are in the equilibrium state. We didn't change anything in the silicon. So it should be as doped. So you have p-type doping 10 to the power 17, then the hole will be the same as 10 to the power 17. And then N, we can always use this NP product. So Ni squared, that is intrinsic carrier density, equals to NP, right? This is always true. So then N will be Ni squared divided by P. And in this class, we assume Ni 10 to the power 10. So this will be given in the exam, probably in the appendix at the end of the question. So you will find those parameters here. So you need to refer to that. And then, then this is will be 10 to the power 20 divided by 10 to the power 17. So you add 10 to the power 3. Okay, any questions? Then let's move on to the second one. What are the electron density N and P, the hole density P, at the interface here when the gate voltage equals to the threshold voltage? Now we apply voltage and make the transistor at the threshold. So if you want to draw the band diagram, then positive voltage push down the band. This is what you apply, Vg. So the band will be bent. So this is EC, EV, EF, and here you have the EI. So it's something like this. And then again, what is N and what is P? I'll give you a few minutes. First, you want to recall what is the definition of the threshold voltage. So the way we define the threshold voltage, first is we say this is a strong inversion. And there are two definitions of the threshold voltage. So first we say this is a strong inversion. And at this moment, the phi s equals to 2 phi b. So what is phi s? Phi s is this bend down of the band here at the surface. This is surface potential, and surface potential moved down by 2 phi b. And also, at this threshold voltage, we say that the surface is inverted from the p-type to n-type, and the n-type electron density is the same as the hole density in the bulk. The electron density at the surface is the same hole density at the bulk. N at the surface is the same as P in the bulk. Surface means here. Bulk means here. So you can actually get this right away because you have done the question 1. So the question 1 we get the P bulk is 10 to the power 17. Now the N surface should be the same as the P bulk. So this one should be 10 to the power 17 now. Because the surface changes from the P type to N type. And by definition, in the threshold voltage, this should be the same. As strong as the P type in the bulk. So this is a strong inversion. So N type is the N type you inverted at the surface is as strong as the P type in the bulk substrate. Then you can also get the P is 10 to the power 3. Now the P, the whole becomes the minority, right? And then again, according to the NP product, then if N becomes 10 to the power 17, P should be 10 to the power 3. All right, any questions here? Okay, then the next, what is the surface potential phi s at the threshold voltage? So this is what we just discussed here. At the threshold voltage, then the phi s equals to 2 phi b. But we need to calculate this one. So how to calculate the 2 phi b? So first, what is phi b? So the phi b is defined here. It's the difference between the Fermi level and the intrinsic Fermi level. So the difference between EI and EF. So Q phi b is like your EI minus EF. This is by definition. So you just need to get the EI minus EF. So there are multiple methods to get this phi b. You can directly use the equation, let's say from the I think we have one here. So you can get the phi b here is the difference between EI and EF. And then you know EF is determined by the doping Na, and EI corresponds to the intrinsic Fermi level. That means intrinsic carrier density Ni. So 2 phi b can be given by this one. You can directly use this one. So you can use this one. Phi b is like this kT log Na over Ni. Of course, you need 2 phi b. And then divide by Q. So you can get the phi b this way. You can also get the phi b by a different method. I think the numbers will be close. You can get the phi b in the other way. So if you think about this is EI, this is EF, and then you have this phi b here. So what you can do is you can get this distance first. This distance is your p-type doping, right? If you recall that distance. So this EF minus EV, over KT. If you negative sign here, that's fine. So this one is your p-type density. So from this equation, you can get the EF minus EV, like KT natural log, and the NV divided by NC, I think. So you get this one. And then phi b will be half of the band gap minus this one. Right, because phi b, you see that is here. This one is half of the band gap, right? EI is half of the band gap. So you can also get the phi b in this way. I think the numbers will be close. May not be exactly accurate, because here, if you recall, in our class we didn't use the accurate number for the NA and for the NV and NC. So there may be a little bit difference by those two methods, but should be close. Okay, so I'll skip the numerical values for the solution. So I just want to talk about the method. And then any questions? Then next, plot the depletion width and surface potential as a function of Vg. Only shows the qualitative behavior. Okay, so this is in this MOS cap. When we increase the gate voltage from 0 to Vt and above Vt, then how would the W change? That is the depletion width. And how would the phi s change? So first of all, we have that conclusion. If you recall one of the true or false question, we said above the Vt, the phi s almost no change. It's almost pinned to 2 phi b. So that means above this Vt, then the phi s is a constant. And also we have the similar conclusion saying that above the Vt, the depletion width also reaches the maximum, Wd max. So also almost no change. So those are two key conclusions from the lecture 8. And then the question is from 0 to Vt, then this part. So this part we need to look at the equations a little bit. So here I think the equations tells you, let's go back to maybe to the lecture 8. So here when we derive the gate voltage as a function of the phi s and W, we have this equation here. And then if we replace W as a function of phi s, then we have this square root. So you see the gate voltage and the phi s here. So and one of the plot we ask you to draw is the relationship between the Vg and phi s. Right, so you are asked to draw the phi s and Vg relationship, but the equation is given there. Here, how do you draw it qualitatively? So you look at this equation. It's complicated, but if you think about what kind of equation this is, what kind of function is this? So here you have a square root phi s And then those are coefficient. You think it's A, and here you have phi s, and then you have Vg. If you think this phi s is like x, square root of x is like x, so it's ax plus x squared. Right. So it's the second order function, parabolic function. So parabolic functions, then you can qualitatively draw this. And if you draw this, it will be something like this. So here we only require qualitative behavior. So it's something like this. And similarly, you can do the W as a Vg, as function of Vg. So we can still go back to here. And when you look at W here, so in this equation, you can also replace the phi s as a function of W, right? So if you plug in this phi s term here, you will say this is plus something W squared. Something is this one. It's something not W squared. So you have W squared W and Vg. It's still a second order function. So still it's a parabolic function there. Okay. Any questions? Okay, then one more question. So again, draw this plot to show the Q depletion and Q inversion. So this is a fixed charge. What contributes to this fixed charge? This is a donor. Sorry, this is acceptor Na minus. So when you deplete the surface, then the acceptor will show the negative charge on the nucleus of the acceptor. And then later when you create inversion, you will have the electron, which is also negative. And then let's draw this, and maybe we should say draw the absolute value of those, because those are negative charge, as a function of the gate voltage. So for depletion charge, we need to go back to this slide again. So the depleted charge, let me say the depleted charge is this one is a depleted charge. This Q total is a depleted charge, QNAW. This is because what is QNAW? So you have the QNA, that is your charge density, but then you have the depletion with W. So in total you have QNAW. This Q total is the depletion charge before the inversion. So this is at the depletion. So you have this QNAW. So you see that this depletion charge is proportional to the W, that is the width. Then you can draw this easily because you have done the width as a function of the Vg, and then the depletion charge is proportional to the width. Then the depletion charge should follow the same behavior. And then this one is like the maximum QNAW, and now this is at the depletion max. Okay, then the inversion charge. So here, how do we draw the inversion charge? That is different. Because below the threshold, then the inversion charge should be very small, because it's p-type, right? Then electrons minority, so it's very small. Only when you are reaching the threshold voltage, then you show the inversion charge. And above the threshold voltage, then we say that additional gate voltage is going to induce more inversion charge, in this case electron. And then it's given by this formula here, I think. Above the threshold, the inversion charge, you see here, if we take the absolute value, then it's the capacitance times the voltage. This voltage is first the gate voltage minus the threshold. This minus is because you have to overcome the threshold voltage to induce the inversion charge electron in this case. So this is you say it's first order function, the inversion charge and gate voltage, but it's offset by the Vt. So in other words, if you draw this function, then it should be a straight line like this. This is because this Q inversion is like COX Vg minus Vt. So only when the Vg is above the Vt, then you will have the inversion charge. Okay, any questions? Okay, then let's go to the next question on the p-n junction. So here we show the depletion region of the p-n junction. And then the first one is at the equilibrium state, so the voltage is 0. And then here we show the depletion charges. So the p-type, after the depletion, then this Na will become Na minus. Then this is Nd is plus. Okay, so here we show the fixed charges by the donors or acceptors. So the question is, for the case 1 and case 2, which one corresponds to which? Let's say voltage larger than 0 or voltage smaller than 0, or forward bias or reverse bias. So the case 1 and case 2, which one is forward bias, which one is reverse bias? So forward and reverse is respect to the p-type. We apply voltage to the p-type, and n-type is always ground. So which one is which? So the case 1, voltage larger or smaller than 0. So this is similar as one of the earlier true or false question. And if you recall lecture 7, we have this animation. This is forward bias. Will apply more voltage, then you will have less depletion width. And then for the reverse bias, this one, when we have more negative voltage, then you have larger depletion width. So if you go back to the question here, then you can tell this one is negative and this one is positive. Okay. And the second one is the p-n junction band diagram. Okay, we have 3 band diagram, and which correspond to which. That means the voltage smaller, larger, or equal to 0, and which one correspond to which. So the first one you see the Fermi level for the p side and n side is the same. So this is we call equilibrium state, and then the voltage should be 0. And then the second one, we see that the p side, the Fermi level is lower. Because we said we are going to apply voltage to the p side. So the n side is ground. So this voltage. And we have a very important conclusion we emphasized many times in the class. The positive voltage push down the band. Positive voltage push down the band. So this is positive voltage. So then here you see this increase. So this should be V smaller than 0, push up the band. So those are the important concepts. And also we said here in this case, if you think about the current, so we have those electrons here, right? So this barrier is lowered, so you have electrons more over to the barrier. So you have the diffusion current. But in the reverse case, then those electrons here will not jump over. But still you have a little bit of electron here. This is minority carrier in the p side. But due to the slope, like water, then electrons tend to move down, fall down. So you have some drift current. This is diffusion. This is drift. Alright, so then we want to draw this IV curve of the p-n junction. We just discussed this diffusion and drift. So if we sketch the IV at 0 voltage, should be 0. No external voltage, no net current. And for the forward case here, once you apply the voltage, then you lower down the barrier. So here, due to the Fermi distribution or the Boltzmann approximation, so here you have a exponential decay function of the probability for the electrons to occupy. The higher level, you have exponentially less electrons. Or in other words, if you move the barrier height down, you have exponentially more electrons move over. So that's why in the forward case, the current is more like an exponential function. And in the reverse case, then this electron eventually will be falling down. But you have only limited number of electrons here because this is a minority in the p side. So eventually all the electrons here fall down, then you will not have more current. So you have a very small current eventually. And this is a diffusion current, dominant. This is this drift current. All right, any questions? Okay, I think that's for the practice exam, and I would say the real exam may have 1 or 2 more questions than this one. So this one is normally for the classroom settings. We have limited time, maybe 1 hour. But since you have 24 hours, so we have maybe 1 or 2 more questions like this for your take-home exam in this case, in this semester. All right, any final questions before we stop here today? I got one. How can voltage and current be negative? So this is possible, right? So here, the negative voltage and positive voltage is respect to the reference, right? So you have your P and N. We always ground the N. If you apply positive voltage, then you have current flow this way. If you have negative voltage, then current flow this way. This is also true here, right? So you see here, in the forward case, then diffusion current by the electrons, you see here, move to the left. But this is electron flow. Then current, by definition, is opposite to the electron. So in the forward case, the current goes this way, right? And in the reverse bias, then electron go this way, and then by definition, current go this way. So this is exactly the same as we draw here. Okay. All right. So then, if no more questions, we will stop here today. Thank you for joining.